The world's so bright, it's hard to breathe, but that's alright. Hush.
Hey guys, this is metacube, and this is the second video in the quantum computing tutorial series. So today we'll be making our first quantum program, and we'll basically be looking at the first gate, and then we'll also create basically a hello world program. So first thing we want to do is we want to open up a Jupyter notebook. So we'll go to our command prompt, and here we'll just type in Jupyter notebook, hit enter, and this is going to give some text, and it's going to open up a notebook in our default browser. So here you'll see all of your folders, and just create a folder that you want. So I'm going to go into the YouTube tutorials, and here, as you can see, we don't have anything so far. So first we're going to create a new Python 3 notebook. So in our notebook we just go here, Python 3, a new file, I guess. Hit that. Bam. Okay. So this is going to be where we program everything. So we're going to go to here, and we're going to name it, I'm just going to call this a gate guide, because that's what we're going to be looking at first. So if you follow along in the series, we're just going to go through many of the gates, and here you can use this as your notes for the different types of gates. So to visualize these, we're first going to import a few things. So first, we're going to import Qiskit, and then from Qiskit, we're going to import, and then star, so that's going to import everything from Qiskit as well. And then lastly, we're going to import something from Qiskit.visualization. So from Qiskit.visualization, we will import plot block multivector. Okay, so it's like this, and we are going to later you can add stuff along, like you can put commas and import more things from Qiskit.visualization, but for this guide we don't need to import that. Multivector, plot block. Okay, and then once we're done with this, just shift enter. Shift enter is just going to compile that in the notebook, and then basically it runs it, and now all this is imported. Okay, so we're going to have to first create a quantum circuit. So to do that, I'll just call mine C equals quantum circuit, and then here we're going to pass through 2, 2. What this is going to do is make 2 qubits and 2 regular bits. We don't need these 2 regular bits for now, but it's just good habit to practice doing this, because you're usually going to always want qubits, or you're always going to want actually qubits and your regular bits, so that once you do your calculation, you can measure your qubits and get a result. If you don't include this, you're not going to be able to store your result of your calculation anywhere. So we're going to perform something called a Hadamard gate. So what this does is it puts a qubit into a state of superposition, which means that this qubit, it's not at 0 and it's not at 1. It is in a state of both. It's equally likely to collapse to either 0 or 1 whenever you measure it. So I'll show you why I'm saying position once we finish this these couple lines, and you'll see why I keep referring them to as position. So we'll do C.H and we'll put 0. So that means I'm performing this Hadamard gate, which is denoted by the H, on the first qubit, or the 0th qubit, since we're programming, and this is all in Python. We're doing this on the 0th qubit, and we just press enter. And then to view how this qubit looks now, we're going to write some code. So I'm going to say I'm going to create a new variable called stateVec. I'm going to set that equal to the result of a function. So function is called execute, and we're going to pass in the first parameter as our quantum circuit, so C and comma, and then it's not doing some sort of algorithm or anything. We just can run this through a simulator because it's only one qubit that we're dealing with right now. So we don't need to involve the actual quantum computer yet. So we're going to set this backend equal to air. If you remember from the previous episode, I said how there were different elements of Qiskit. Air is involved with the simulators. So the quantum computing simulators, you will see air thrown in somewhere around there. So we're going to do air dot get backend, and then to that I'm going to pass in a string, and I'm going to call that state vector simulator, not simulator. Okay, and then from that we want to get the result, and then from that we're going to say get state vector. So this all seems very, very complicated, but in the end it gives us a simple result. So let me just run that real quick. So now this is stored in the variable state_vec, and all I'm going to do is I'm going to say plot block multivector, and then to that I'm going to pass in state_vec. Oh, my bad. Not block, it's block with an H. Okay, so when we run this, now let's look at this. This is pretty interesting. We see qubit 0, and we have qubit 1 since we have 2 qubits to start with. Qubit 0 is in this, it has this arrow that's pointing directly to the x in the x direction. Okay, it's pointing to that x in between 0 and 1, and qubit 1 is pointing just to the 0 state. Okay, so this is what I meant by position. Whenever we perform a gate, we're just going to think of it as some sort of rotation or manipulation of this vector or arrow in this three-dimensional sphere. So the default of all the qubits when we first create them in our program is going to be this 0 state. So the arrow is going to be pointed at the 0, and it's not in any direction, just straight up the middle. Okay. Then if we perform a Hadamard gate onto one of those default qubits, we get this arrow pointing into the x direction. And if we see, once again, it's just straight in the middle. This means that whenever we measure this qubit, it has to collapse either to 0 or 1. As of now, it's in this superposition state where half the time it's going to collapse to 0, half the time it's going to collapse to 1. But we don't know which one it's going to be until we measure it. So it's going to put any default qubit into this position. So this is going to be the key gate that we use for our Hello World program. I'm just calling it Hello World because it's like the first program that we're ever writing. So now let's go to the actual program that utilizes this gate. So let's just save this, and then I'll just exit out of this. And then from here, let's create a new one, and we'll call this the Hello World program. Or you can call it first or whatever. I'll just call it first program. We have our first program notebook open. So we're going to start off with pretty similar import statements. We're going to start off by importing Qiskit, and then from Qiskit importing everything. So we do that with an import star. And then we're going to do one additional import from last time, which is from Qiskit.tools. We're going to import something called job monitor. What this is going to do is when we're running our program on a real quantum computer, this is going to tell us when the job is still running or if it's still getting validated or when it's done. So that's all the job monitor is going to do. And then lastly, we're going to import from Qiskit visualization. We are going to import not a plot block multivector, but instead we're just going to import plot histogram. This is going to be the usual way of visualizing our results, as it'll give us a bar graph representation of the results. It'll show the number of times each state was achieved. So out of 1024 tries, if we get 500 times, we get a 0, 500 times, we get a, or 524 times, we get a 1. That's one of the possible measurements. So we'll see an example of that when we run our program. So these are our import statements. We just run them, everything will get imported. And then from here, we're just going to first create our circuit. So C equals quantum circuit. And then here we don't need 2 qubits, we actually only need 1. Last time we did 2 so that I could show you the difference between the Hadamard qubit and the default qubit. But for this one we only need 1, and then we're going to read out our results onto a regular bit, so just one of those. So I'm going to perform a Hadamard gate on that single qubit, and then from here I'm going to measure the circuit, which will basically complete all the gates, and then when you measure the qubits, it's going to collapse them into their respective probabilities. So once in a superposition, like our first qubit is, it's going to make it decide essentially whether it is a 0 or a 1. And then here, you're just going to have to put this in brackets, this in brackets. This just shows that the 0th qubit, you're mapping that to the 0th regular bit. So what we can do is we can run this, and then if I do c.draw, it'll show us this little diagram. So that shows the 0th qubit, and then the c_0 shows the 0th regular bit, and then this H block, that is the Hadamard gate that we're performing, and then after that we see there's an M that leads from that qubit to the regular bit, which shows that we're measuring and we're storing the result in this regular bit. So now let's run on one of IBM's quantum computers. So first what we're going to do is load our account. So we're going to say IBM Q dot load account. So if you recount in our first episode, I said that we have to do this on every new file or notebook that we create. So this is a new file, so we have to do this step. And then from here, I'm going to say provider equals IBM Q dot get providers or provider. And then here I'm going to put hub equals IBM Q. So dash Q. Okay. So then I'm going to have to execute this program and then store it in a variable. So I'll call this job. I'll call this variable job, and I'll set that equal to execute. So that's the function that actually runs the program. And then the first parameter is going to be our circuit that we're executing. And then I'll say backend equals provider dot get backends. So here I'm just going to give you one of the backend names that we can use, or one of the quantum computers that IBM provides, which is IBM Q Burlington. If I'm just doing some tests like this, I like to use Burlington because it's actually not used that much. It has 5 qubits of storage, and then we have to say how many times we want to run this program. Because if we run it once, it's not really going to tell us much. Because let's think about this. If I run this program once, when I measure it, it's either going to be a 0 or a 1. And since I ran it one time, it's not going to make that much of a difference. We just know that we tried it one time, and quantum computing is all about running something multiple times so that we can find the best answer. So here I'm just going to say 1024. It's a default number of shots that you'll find if you use the drag and drop version of Qiskit. So then after this, I have the job running. So now I'm gonna want to pass a job within the job monitor function so that we know when this is getting validated, when it's running, blah blah blah. And then lastly, we have to view our results. So I'm going to say plot histogram, and then I'm gonna pass in job.result.getCounts as the parameter. And then here, if I shift enter, this is actually now communicating with the IBM quantum computer. So it's going to take a while. Before, when we were using the quantum simulator, which is called the Chasm simulator, it almost immediately ran really quick. Oh, what is this? Oh, forgot the underscore. It's very important. So, as I was saying, this one will actually take some time because it's communicating with the quantum computer, and if there are other people waiting in line to using this quantum computer, then it's going to take a while until they're done. But the simulator just runs and it doesn't depend on anyone else, so you don't have to wait for that. So now we have our histogram results, and here we can see that about half the time the result was 0, that qubit measured out to be 0, and then half the time about the measurement came out to 1. So why didn't it come out to exactly half? Well, this is quantum computing in real life. This is not a simulator. There's going to be some noise present in the quantum computer. So these quantum computers, when you take their measurements, since they're at the atomic level, they're going to have slight errors in whatever they do. So unless you have the perfect quantum system, which we don't have access to as of now, then the results are not going to be pinpoint accurate. So that's why you get this. Our case, it was 4 thousandths of a percentage, I guess, of error that we had. So in small programs like this, the error is very, very small, of course. But as you go to more and more complex programs that actually take more time to run, you're going to have more and more noise involved. And sometimes you'll get to a point where the noise corrupts the data that you get so much that you can't easily tell which one was supposed to be the answer to whatever problem you had, or whichever one was just invalidly raised up, or the probability was raised down because of the noise. So in later episodes, I'll show you how to mitigate that noise, which is the job of Qiskit Ignis. That's another element of Qiskit. So Ignis deals with noise mitigation, which is a big part of quantum computing. So as you can see, this step right here, these steps right here, it'll kind of get redundant if you just keep doing this over and over again for every computation. So if you look in the top right corner, you'll see I have a video linked where I use a function that I created where it'll search through. So if you just put in run program, and then the parameters of the function will just be the circuit you want to run. And if you're trying to get a vector, like a plot block multivector, if you're trying to plot that, that'll be an option that you can put as one of the parameters. Or if you're trying to get a state vector, or if you're just trying to run the program as usual, that's one of the parameters that you can choose. And then the number of tries or shots that you take, that's another parameter. So in that video, I'll be showing how to create that basically God program, which I just copy in all of my other quantum computing programs so that I can just easily run the program without having to do these steps over and over again every time I want to run. It makes life so much easier. So as you can see, this is the most basic program, I guess, we can run on a quantum computer, where you have just a Hadamard gate, and you basically see how 50% of the time the measurement comes out to 0, 50% of the time measurement comes out to 1. So if you like this video, remember to like and subscribe to the channel for more, and stay tuned for the next video. Thank you for watching. See ya.